Hey everybody, welcome to part 2 of our webinar about navigating the artificial intelligence revolution in industrial predictive maintenance. I'm Andy Zimmerman. I'm the Chief Technology Officer here at Grace Technologies, and I am again super excited to come back and kind of wrap up this exciting and relevant topic. Before we get into the nuts and bolts of the presentation, I want to cover a couple of kind of housekeeping issues. First and foremost, please ask questions throughout the course of the webinar. Feel free to just mount those in the chat bar that's present on your screen. I won't address those during the talk, but at the end, we'll cover any and all questions that come in during the presentation or during that Q&A session. And I will remind everybody that the recording of both this presentation as well as the part 1 from Tuesday will be made available on demand, not immediately, but soon in the next day or two. So Nick will get those sent out to everybody that's registered from there. So with that, let's kick in and start part 2 here. So the first section here is going to be redundant to those of you that sat through part 1, but I want to give again a little bit of an introduction to who I am and what we're going to be talking about today. Again, my name's Andy Zimmerman. My background in this space comes through my work really at the University of Michigan, where I did my PhD in structural engineering, focused on building kind of AI and low-cost, low-power wireless systems for monitoring structural engineered things. So bridges, buildings, ships, wind turbines, that sort of thing. And that focus was really around distributed data processing in wireless sensor networks. So from there, I went on and started a company called Sivionics, where we took that technology out of the university and started applying it to structural health monitoring and industrial Internet of Things applications. That company was sold back in 2018 to Grace Technologies, and so I'm happy to sit here today wearing a Perceive hat. Perceive is the entity inside Grace, our subsidiary that has managed a lot of the work that we've done underlying the analytics in the GraceSense line of products, and really has been focused on AI and how it plays into predictive maintenance over the last kind of 4 or 5 years. All right, so before I get into the nuts and bolts, I do want to throw another shout out to my collaborator, Chao Hu. He has been kind of a major partner in this AI-based research over the last 5 years, originally at Iowa State University, now at the University of Connecticut. And he and I have been really working a number of kind of grant-based research topics that all focus on predicting the failure of rotating equipment, specifically bearing failure, using deep learning-based techniques. That work's been funded by a number of agencies, including the state of Iowa, most recently the National Science Foundation in a phase 1 and a phase 2 STTR, and then also Grace Technologies and some others have contributed funds to that work. So I want to just give a major shout out to all those folks. So we won't go into any of that detail really here today, but this kind of underpins why we're talking about this subject matter today. All right, so why this webinar and why now? Again, this is same slide I presented on Tuesday, but the idea behind presenting this now is that AI and machine learning are really poised in today's world to significantly transform the industrial predictive maintenance landscape. And it's really setting the stage to do that in a variety of ways, but kind of foremost amongst them is its ability to drastically reduce downtime in the industrial facility. Additionally, the pace of innovation in these spaces is rapidly accelerating. We're seeing new applications and new technologies emerge almost every day in this world. And as a result, we're really starting to see a tremendous number of new challenges that society hasn't faced before emerging alongside these new AI ML technologies. So these things range from data management to the cost of implementing AI technologies to ensuring that your data is private to being able to actually interpret results that are coming out of these AI ML systems. And today we will spend a large part of the webinar discussing those challenges and some potential strategies to overcoming them. So the last reason why we're talking about this is really that this future is now. A lot of these technologies that I discussed in an application sense on Tuesday, and that I'll talk about in a little bit more detail today, these are things that are emerging. They're present right now. They're being used. And so it's important for the industrial community to be aware of what's happening and be able to start leveraging these technologies to enhance our predictive maintenance world. All right, so what do I expect out of this webinar? First and foremost, I'm assuming that most of you that are watching this today come from the perspective of industrial predictive maintenance, or at least industrial maintenance. You see the potential in that industrial maintenance world for artificial intelligence to make some really create some ground-changing benefits. But at the same time, you have some questions about how AI is going to play into the industrial space and how these new technologies can integrate with the types of work you're doing today. So on the flip side of that, what you can expect from me is that this is, as I said last time, this is a huge topic. It's very difficult to comprehensively discuss AI, but that's kind of what we're trying to do today. That's why we broke the webinar into two parts. We're really just trying to present a high-level, comprehensive overview of how artificial intelligence and machine learning can impact the industrial community. So I'll be presenting that in kind of an AI ML 101 style. So if you're an artificial intelligence expert, a lot of what I'm going to say today is going to be pretty high level. I'm really trying to touch on big concepts, not specific details. And then lastly, this is not a product focused webinar. I'm really just trying to provide some information here. We did a demo at the end of the last section, and I'll talk a little bit about how we have some products related to this at the end of this one, but generally this is just an information section. All right. So at this point, with part one, we covered the evolution of maintenance, kind of how maintenance has moved from a reactive world into a preventative world or a condition-based monitoring world. And then we discussed how AI and ML can really change that ecosystem into a truly predictive one. I also touched briefly on a demonstration of how generative AI can be used to assist a maintenance team in their maintenance tasks. And so we're going to kick off part two here by getting a little bit more detailed in our understanding of the technology behind what's been discussed, the challenges and the opportunities that kind of surround those applications and really the artificial intelligence and machine learning space as a whole. So that's enough of kind of introduction. Let's kick into the main content here. So for starters, and this is again redundant, but let's do another task at presenting what AI is and giving it some definition. So first and foremost, artificial intelligence is almost always going to come from a computer system of some sort that's going to be capable of learning from data, taking that data and the learnings that came out of it and making decisions, and then ultimately performing some sort of task that has historically required human intelligence to complete. So just to reiterate, it's a computer system that's performing some task that used to, in our past lives, require a human, at least in some capacity, right? And there's a lot of ways we can apply this in the predictive maintenance domain, from predicting machinery failure to recommending kind of maintenance tasks to interpreting image or video in our facilities or understanding, natural language on a conversational level. And today, what we're going to do is dive into kind of some of the underpinning tenets that sit underneath these applications. So I'm going to start by talking about 5 kind of what I consider to be main topics or main ideas that are prevalent within the AI space. And I think it's important to understand each of these in at least a little bit of detail to talk about artificial intelligence or machine learning in detail. So the first of these, we didn't really talk about this in part 1, but is machine learning. We'll move on from there and talk about neural networks, then talk about how deep learning plays into that ecosystem, and then finish off by talking about classification and regression problems. And then from there, we'll move on to talk about some opportunities and challenges. All right. So machine learning. This is a subset of artificial intelligence that's going to provide our computing systems the ability to automatically learn and then improve upon their learnings based on experience that's coming from data without a programmer sitting there and explicitly programming that knowledge into that computing system. So we use statistical methods, and then we enable those machines to actually improve with experience. So we break this down typically into 3 main types of machine learning. The first of these is supervised learning. In this particular approach to machine learning, we take a machine learning model and we train it using a data set that's labeled. So a good example of this is your spam filter. If your spam filter's been built using machine learning tenants, we basically, what has been done is a set of email has been provided to it, historical email, and each email has been classified either as spam or as not spam. And then the machine learning model is going to pull the new email that comes in and assign a label, either spam or not spam, depending on kind of that historical knowledge that we're building from the data that's come in on those previous emails. You okay, Nick? Okay. All right. Second main machine learning type is unsupervised learning. So this is the flip side of a supervised approach, where we're going to actually train a model on an unlabeled data set. So we need to actually use the machine learning techniques themselves to find patterns in this data on their own. So a good kind of common example of this is Netflix or Amazon making recommendations based on previous use case from that user. So if I have previously bought products X, Y, and Z on Amazon, and the machine learning algorithm can actually look statistically at what other users who have kind of bought those products and potentially fall in a similar demographic group to me have bought, it's able to make inferences on what I might like to buy next based on that kind of set of unsupervised data that it's been given. So there is no actual classification happening. It's using similarity concepts to drive its training process. So the last kind of main type of learning that you'll encounter in the machine learning space is reinforcement learning. And this is what's been used heavily in a lot of the kind of game-based development. If you see an AI that's playing some sort of game, more often than not, it's been trained using a reinforcement technique. So this is where that model is going to interactively learn with its environment by receiving either rewards or penalties or both based on the actions that it takes in that environment. So examples of these are DeepMind's AlphaZero and AlphaGo, which are capable of learning from scratch how to play complex games, in this case chess or Go, just by playing hundreds of thousands or millions of iterations of a game and being rewarded when they make a good move and being penalized when they make a bad move. And those rewards and penalties over time can serve to train a machine learning model to actually play these games at a level that's greater than any human. And so this is a very powerful way for training certain types of machine learning models. All right, so the underpinnings of machine learning generally sits in this concept called a neural network. I'm sure you've heard this term, but I'll get into a little bit more detail here. Again, surface level, but more detail than you'd have if you haven't seen this concept. So a neural network is a computing system that's been inspired actually by the human brain. That's why we call it a neural network. These networks are composed of layers of neurons. So on this image that I've got here, each dot is a neuron in that network. And those neurons are responsible for either processing or passing on or doing both information that's kind of coming from left to right in this network. The key components to this any sort of neural network is going to be the input layer. So this is where we're taking our data stream and we're gonna push it into the network, whatever that data stream might be. That could be my shopping history, for example. We then have a set of hidden layers. These layers they sit between the input and the output, and they're generally used to perform kind of simple computations that are going to transfer information from the left to the right. I mean, we'll get into a little bit more detail about this later, but the idea is that these computations are what get trained in this network. Then on the right side of any neural network, you see your output layer, and that's going to be the results that the neural network is providing. So in the case of my shopping example, I put my shopping history, for example, on the left side, and out the right is going to give me some suggested products to buy. That's how this network works. And then when we train one of these neural networks, this is the process by which we adjust the parameters in those hidden layers using kind of known inputs and known outputs, depending on which kind of learning technique we're using. And in the end, what we're trying to do is produce accurate outputs for a given set of inputs, right? I want when I put my shopping list in the system, I want to be able to get a good set of recommendations out the other end. So the goal of any sort of training is to create a network that reflects reality as closely as possible and gives the best possible predictions in as many cases as possible. So if we take the neural network and the machine learning concepts and kind of drive them in a application or application specific way, we end up inevitably talking about deep learning, which is another concept I'm sure you've heard in kind of common parlance over the last few years. This is a subset of machine learning where we're using neural networks to learn from vast amounts of data. So in some simple neural networks, you could have only one or a couple layers, but generally in a deep learning system, we're going to have potentially hundreds of layers that are going to allow us to learn and then execute on super complex patterns in data. The kind of applications that we see here, specific to predictive maintenance in this particular case, are A, pattern recognition. Okay, so these deep learning networks are capable of really recognizing complex patterns in machinery performance or the sensor data that's coming in, and we can use that deep learning network's understanding of those patterns to detect when things are wrong, right? Secondarily, we can do advanced predictive modeling. So we can create really highly accurate models because of the number of parameters that can be trained inside these models. An example of that, if you look at OpenAI's ChatGPT, I mean, there are potentially trillions of parameters inside that model that are being trained, and that allows it to perform in an incredibly complex way. And we can also do really advanced image or sound analysis, where we take visual or audio input, and we're detecting issues that maybe are not easily captured by traditional sensors. So this, in addition to some of that generative kind of AI stuff I talked about in part one, these are major applications for deep learning. All right, so next kind of concept I want to lay on the table is classification. And we did talk about this in part one a little bit, and it's been mentioned offhand, and I think it's fairly intuitive to folks what this means. But classification is generally going to be a type of supervised learning where the output is a category or a class. So in the predictive maintenance space, that's typically you're looking at, healthy, not healthy, right? Or healthy, kind of healthy, not healthy. These categories can be anything, and they can be as numerous as you want. But the idea is we're building classification algorithms that are going to take training data and use it to classify new observations into those classifications that we've set up. So my example here is basically a very simple classification problem where we're trying to figure out if a dot is black or white, right? And you can see in both of these images on kind of one side of this line, the dots are black, and on the other side, they're white. So what the classification approach is doing is it's trying to find where to place those lines so that when the next dot comes in, it's pretty obvious which category that particular dot falls in, the black or the white. And this gets significantly more complex when you have, kind of more than two axes in this particular problem. But for now, just think about it like this in a kind of two-dimensional way. And what we do a lot of times is we try to take that boundary, which is squiggly on the left, and then find mathematical ways to represent it as a very clean boundary, like you see on the right. And that enables us to do our classification in a much, much easier way. So there's a lot of ways I'm sure you can see that this is used in the predictive maintenance space. First and foremost, fault diagnostics. I already talked about that, categorizing things as either healthy or not. We can also use data that's coming in from our equipment and basically categorize the risk level of that piece of equipment failing based on the information that we're seeing. So this allows us to do a risk-based analysis of where our maintenance needs to be headed. And then the last thing here is actually using a classification approach to recommend certain maintenance actions. So if you were to train a model on the optimal maintenance approach for a given set of input data, we could actually, the output of that could be just a straight recommendation for some sort of maintenance. And that would be the classification is either no maintenance or, lubrication, you need a bearing change, you need an alignment, whatever the issue is, we can classify in that sort of way. So this is one major way in which machine learning specifically is being used to drive artificially intelligent systems. So I'm going to give a very specific example here, and this comes from the research that we at Perceive have been doing with Iowa State over the last few years, where we're really trying to, in this case, classify what type of damage, if any, a specific rolling element bearing has been seeing. Right? So this is an example of a deep learning approach to classifying bearing damage. So if you look at a bearing, like I've got shown here on the screen, there's kind of several ways in which this particular bearing could see degradation or damage. And it generally occurs by some sort of cracking or pitting in either the ball itself in that rolling element bearing, or the inner race, the outer race, or the cage. Those are kind of the three main ways in which a bearing can degrade. And so our research here was really looking at, okay, can I take vibration data from that bearing and be able to classify whether that bearing's healthy, whether it has an inner race fault, an outer race fault, or some combination of these kind of different types of faults that we can see. I'm not going to get into this kind of image at all, but you can see here the way that works is kind of this physics-inspired convolutional neural network. And this particular network is a layered system that allows us to take that vibration input data, filter it in a very specific way, and then output a health class on the right side of the network. And in the end, this very simple kind of test matrix you see at the bottom, this is how we kind of validate whether this is working. So we run a bunch of different examples. On the left is the true label, the actual health class of the bearing that we're talking about. And on the top is the predicted health class. And you can see that in this particular example, in almost all cases, our physics-inspired convolutional neural network, was able to identify which health class the particular bearing we were monitoring existed in. Now, I will say that this was done under very clean data, so you generally don't see 100% success in these systems. And we, if you're interested in that paper, reach out to me. We can push you to the more complex analysis we did. But this is generally how a generic classification problem would work. All right. So moving from classification to kind of the other type of main output in the predictive maintenance space, this is when we start talking about regression. So this is a type of predictive modeling where we're going to estimate a relationship between one variable, a dependent variable, and one or more independent variables. So you can see this plot on the right where we've got a bunch of data. The idea is to, if I know my Y value here, to be able to predict the X value or vice versa, depending on the application. And the goal here when we're doing regression is to be able to kind of match that curve and then predict a continuous outcome from where that data sits over time. So where can this be used? This has kind of been talked about quite a bit in the last couple of parts, but we can use regression-based techniques to forecast the remaining useful life of industrial equipment. Right, this is using historical data to then train a model on what that data is going to look like moving into the future. That's a regression-based approach. We can do the same kind of thing for inventory levels, right? And this was brought up in the Q&A session in our last part, where it's well and good that we can predict when something's going to fail, but if we actually can't predict whether we're going to have the replacement part in time, that may defeat the purpose of predicting the failure in the first place. So I think there's a lot of applications that are going to start to emerge for AI and ML in inventory management and supply chain applications. And then lastly, I think regression can be a really powerful technique from a maintenance perspective when predicting the costs associated with a maintenance program. So this allows us to do a better job of budgeting for what maintenance is going to look like over a period of time, and then along with that budget, planning out resource allocations and scheduling maintenance and all of that. If we have a solid AI-backed way to forecast our cost structure moving forward, it makes a lot of these more kind of business level decisions a lot easier. All right, so here's an example of, again, some of the research we've been doing with Iowa State over the last few years in its ability to predict the remaining useful life of bearings. So this was a deep learning approach, again, not to classifying the health of a bearing, but to actually predicting what's going to happen to that bearing in the future. So when you're looking at this plot, I want you to first focus on kind of this top plot. This is showing the overall vibration level of that bearing that's under test. And that vertical line, you see, it's kind of a dashed vertical line. Think of that as right now. So everything to the right of that is the predictions that the model is making. So up at the top, we're going to have some sort of maintenance threshold. And if we're doing condition-based maintenance, typically, we've got these thresholds, and we're going to alert a user when that trend hits that threshold. So the difference here is that I'm not waiting until I hit the threshold to alert the user. I'm telling the user, hey, there's a chance that you're going to hit this threshold in the next 45 to 60 days, right? And our predictive models are showing, that probability of threshold level exceedance is going to fall, kind of in that 1 to 2 month window, right? Now, the next thing I want to pull your attention to is the second plot there, the green one. This is the part of the vibration analysis that relates to the lower speed or the shaft speed related dynamics. And you can see here that our predictions are that is not changing drastically. We don't expect that to ramp up much in the future. And that the information that we get from that is that, yeah, you're going to need to maintain this piece of equipment over the next kind of couple of months, but it's probably not an alignment or balance problem, right? If we look at the bottom plot, however, which is focused on the higher frequency dynamics that typically relate to bearing problems, we can see that those dynamics do trend with that kind of 45 to 60 day window. And in this case, we can say fairly confidently that it looks like this particular bearing is going to, this particular piece of equipment is going to experience a bearing problem over that kind of 45 to 60 day timeline. And obviously, if you're running a maintenance team and you have the ability to forecast that out, it makes it a lot easier to plan when you're going to maintain that piece of equipment. All right. So the rest of this presentation, now that we've kind of taken some time talking about the nuts and bolts, is going to focus on what are the remaining hurdles to kind of take this sort of AI technology into practice in the industrial space. And I won't talk about these on this slide because we're going to touch each one in greater detail over the next maybe 10 minutes here. So let's start with implementation costs. This is one of the big issues right now with getting started with AI in the industrial setting. The initial setup of any AI ML system is going to be expensive, almost certainly. And it's going to require upfront capital to get moving. There's just no way around that because it's generally new technology. It is also going to require ongoing maintenance costs to keep it running effectively and efficiently, and even more than that to run it optimally. Right, so we're going to need to pay for system updates, for data management. We got to train users to be able to effectively use it. So there is an ongoing cost to any sort of AI ML solution for sure. And one of the things we run into with our customers a lot is it's very difficult a lot of times to put a good return on investment number on an AI ML implementation. It's not necessarily immediately clear what that AI is going to do, and that may make it hard to put that kind of upfront money on the table. So I'm going to turn that around, though, and talk about opportunities. Right? Let's say we take this hurdle. It's going to provide, a variety of benefits to that company. First and foremost, long-term savings. Predictive maintenance in general can lead to enormous cost savings just by predicting catastrophic failures before they happen. The typical example here is if you have an application that costs you $10,000 per hour when it's down, and it's down for 3 hours every quarter, right? Well, if you're able to prevent one downtime incident and that system costs $30,000, it's paid for itself. Secondly, using AI ML for predictive maintenance can really improve efficiency. So in addition to just detecting these errors, it can help point out better ways in which we can maintain our equipment, which will lead to overall improvements in operational efficiency, which coincidentally also help with cost savings and increased profits overall. And then lastly, I think the first movers in this AI ML space, at least those first movers that are able to effectively implement AI and ML in their kind of industrial worlds, they do have a competitive advantage because it will give them a leg up in a variety of ways over their competitors that don't have access to that same kind of technology. So implementation costs are challenge number one. Challenge number two is technology integration. And this has been the case with all of the condition monitoring technology that we've seen at Grace. And it continues to be with AI and ML. how do we actually integrate these new technologies with our existing legacy industrial systems? The main issue here is that existing infrastructure, especially in the industrial world, is almost certainly not compatible with new AI and ML technology. Especially today, if we look at it right now, there hasn't been a lot of movement to try to bridge that gap. So you tend to see the AI ML technologies being developed in a bubble outside of the industrial world. And as a result, that's going to require, complex or costly updates to existing systems in order to get everything integrated. There's also almost certainly going to be a skill gap in the industrial world where most manufacturers lack the in-house technical skills necessary to easily integrate these new systems. There's going to have to be new training on how to use this stuff. And none of this is rocket science, but it does require a change of focus from kind of the way that maintenance has been running over the last several decades. And then, ultimately, generally, when you put in a system that's this kind of earth-shattering, you will see disruptions of current processes. Implementation of new technologies can almost always establish, routine workflows and force the maintenance workforce to do things differently than they have historically. But if we turn that on its head, I think this technology has the potential, if properly integrated, to really streamline that maintenance process, which in the end will reduce downtime and improve on efficiency, like we talked about on the last slide. I think it allows us to make better decisions as those responsible for maintaining assets. If we can integrate this properly again, we can provide comprehensive real-time data to the maintenance team, which ultimately aids in the best decision-making possible. If you know what's going on in real time, and even better, if you know what's going to happen in the future. And ultimately, an AI/ML system kind of sets the stage for continuous improvement. If we integrate this level of technology now, that really will be a first foray into the ability to kind of continuously integrate on this technology as it moves out, as new tools and new techniques become available. So that's challenge number 2. Challenge number 3 relates to data, and specifically the quality of that data and the management of that data once it's collected. The problem that we typically see with data collection is that it's either inaccurate, it's bad data coming from sensors, or it's incomplete. And if we have either of these scenarios and that data quality is poor, that your artificial intelligence is only as good as the data that you're pumping into it. So if you have bad data, it's going to lead to bad predictions, bad classifications, and ultimately suboptimal decisions. We also run into a problem with data where it's siloed. So you may have multiple systems collecting data, and that data is not integrated well. If this is the case, we also run into inefficiencies because that AI really functions best in most cases if it has a comprehensive view of how the ecosystem is functioning that it's monitoring, right? So getting data into a single data lake is an important part of an effective AI/ML implementation. On the flip side of that, right, if we successfully get this data collected, that high quality data can really improve the accuracy of any AI/ML model, and it will lead to better predictions. A lot of times, quality data can actually overcome an AI model that's maybe not the best, because that AI model, if the data is clean, that technology is pretty capable of making good assessments based on data that's coming in. Another opportunity here is just holistic insights. If we have good quality data that's managed properly, it's going to enable our comprehensive analysis of everything across the facility, right? So even if we're focused on monitoring some sort of critical blower, for example, getting this technology in place will eventually allow for a comprehensive view of how the facility is operating, and ideally, that comprehensive view will provide some holistic insights that drive value across an organization. And then lastly, if we have good data, it's going to aid the trust of anyone who's kind of looking at that data. So if we have compliance requirements that enforce the need for good data, or if you've got a maintenance technician or a maintenance manager or an executive that's looking at an AI-based system, if that data is clean, correct, and well stored, it's pretty easy to point back at it when you look at the results of an AI/ML algorithm and say, look, the human can make the same assessment as the AI. If the data is messy, it gets a lot harder to kind of draw that together. The AI becomes a little bit more of a black box. So This challenge here, the fourth challenge, is related to the last one because it deals with data. And here we're going to talk about cybersecurity. So first and foremost, I think as we collect more data, this is true of condition monitoring as well as AI ML. The more data we have, the higher the risk that there is a breach of that data. Now, in the kind of condition monitoring or AI ML space, we're not dealing with personally identifiable information generally. So, maybe this is not as critical, but we do have customers that are very concerned about the privacy of their equipment data because of potential competitive issues or other reasons why that data needs to be containerized inside a facility. So this is a challenge that needs to be overcome. Additionally, we're starting to see regulation emerge that's going to require companies to protect certain types of data. And if you fail to comply with those regulations, that can result in both hefty fines or other public kind of ramifications. Now, again, in predictive maintenance, this is maybe not as critical as other spaces. One of the places this is popping up is, let's say you have an AI that's helping an insurance company choose whether or not to insure something. This is a place where regulation may require that insurance company to make sure that its data is maintained privately. So on the flip side of kind of the hurdles of getting involved with a quality cybersecurity practice, this does give any user a competitive advantage. If you're able to put in a truly secure data lake, this will demonstrate compliance with any sort of regulations that apply, but also just give your customers kind of peace of mind knowing that you are able to deal with data and perform these kind of advanced analytics in a way that's reliable and trustworthy. There's also an opportunity in some emerging technologies. So I was going to talk about this and then decided not to, but there are some mechanisms evolving, federated learning being one of them that we've played around with a little bit, that are going to enable AI and ML approaches to exist without data sharing between entities. So to give the example there, if you have two plants and you've got data from both of them that might benefit the building of some sort of predictive model, we can actually use a federated learning approach to train those models locally and then have those models kind of coordinate up a level without actually sharing any sort of identifiable information that went into the training between plants. So that's kind of one of the things to look for in kind of the coming years are these abilities to decentralize training to protect data. Okay, this is my last topic here, and it's the one that maybe is the most kind of influential to me, the one that's top of mind for us here at Perceive and Grace, and that's this challenge of explainability. So when we talk about AI in general, models have a tendency to be very complex, especially when we're dealing with deep learning. And those models, as a result, are super difficult to interpret. So if I classify this thing as healthy, it generally is very difficult for a human to go back to that model and figure out why the model said that this thing is healthy, right? That takes a lot of effort. On the explainability side, there's also this trade-off between accuracy and explainability. So if I have a highly accurate model that's giving me excellent results, that tends to be a more complex model. And as a result, it's less interpretable. So there's this like trade-off between I want it to be super accurate and I want to be able to understand why it's making the decision that it's making. And lastly, I think there is going to be a regulatory challenge here as well. Certain industries are starting to put regulations in place requiring a level of explainability. And this may make it challenging in some places to implement AI models. Now, I don't necessarily see that happening in the predictive maintenance space, but let me go back to my insurance example. If we have an AI that's aiding an insurance company in making a decision about whether to insure someone, there are regulations starting to emerge that are enforcing the fact that decision is being made without any sort of discriminatory practice underneath it, right? So if that model is somehow using protected information to make that assessment, and there's no way for that insurer to point back at the fact that model is not doing that, that's potentially an issue in that space. So again, I don't see that playing out quite that way in the predictive maintenance space, but it's one that you should be kind of aware of. as AI continues to take off across industries. So on the flip side of these challenges, an effective explainable AI approach can definitely generate trust and confidence in users. And this is huge in the predictive maintenance space. So if we've got maintenance technicians or maintenance managers who truly understand the decisions that are being made by the AI model, that makes that AI partner more of a trusted resource and less of a black box. So it also, by explaining these models, that inevitably is going to lead to better model development. So if our models can do a better job of explaining how they're making decisions, that allows the human to kind of come in the loop and help improve the design of the model and the ultimate performance of that model moving forward. So explainability is a big topic. I'm going to throw a slide. Oh, I got one more here. Regulatory compliance. I mean, this touches on what we just talked about, but in industries that have these regulation requirements, obviously, if you don't have explainability involved, you might not be able to play with AI in that space. So it may be a requirement. Okay. So last thing I'm going to do here is give kind of a quick example of one of the ways in which we've played with explainability in this kind of bearing world that we've talked about. So explainable AI, XAI in general, is going to refer to methods and strategies in the application of some sort of AI that's going to result in that AI solution being understandable by human experts, right? So this is in contrast to the more black box approach to AI, where you have a neural network that's taking in input and putting out some output, but there's no way to understand or interpret what's happening between input and output. So the idea here is really we're driving that level of trust in the human. So in predictive maintenance, this is going to allow us to understand decisions better. Operators, decision makers can better understand what the AI is doing and make decisions from there. It's going to let us verify the soundness of our models. So if you're a expert that's actually helping create the model, the explainability piece of the puzzle is going to allow that expert to examine the logic behind the AI model itself and ultimately increase the confidence in that model's validity and reliability. It's also going to, explainable AI will provide explanations that allow it to align with the technician's experience and expectations, right? And if we do this, this is going to help build trust in that technician in, that the model's outputs moving forward. And then lastly, if we have explainability as a main piece to any AI system, it's going to drive AI models that can be communicated more efficiently between maintenance workers, between maintenance to management, and kind of all the way across the organization. So one example, just to give you a little bit of context of how this works. This is a paper that came out of Nature's Biomedical Engineering journal. This was a few years ago, and we've been using some of these concepts in the bearing world, but I think it's easier to see in this environment. So this is a set of intracranial kind of X-rays, right? So these are scans, CT scans of a human skull, looking for signs of intracranial hemorrhage. And I'm not going to get into any of the medical because I don't understand it. It's not my world, but imagine that there's kind of two types of hemorrhage that you can have here. You can have a red hemorrhage or a blue hemorrhage, and you're seeing at the top there that over the set of data that they're looking at, they're classifying a probability that a given image has a given type of hemorrhage. In this case, the blue is up in the blue section, the red is up in the red section. It travels right with that, right? So you have a visual probability of that classification, right? And this could go to a doctor. You could put your image into an AI system and it would say, hey, you have a 100% chance that you have a blue hemorrhage, right? But that's potentially difficult to trust if the doctor doesn't know why that decision's being made. So this paper goes in and it actually uses kind of a visual explainability method to show that doctor, that physician, the rationale behind the AI's decision. So the first kind of level of this is it's going to visualize the locations of what it's pulling out of the image that's being analyzed. So that's this first kind of layer here is it's saying, hey, these areas of this scan are what are concerning to me. And then the second stage is it's going to drop down and it's going to pull similar scans and show the doctor, look, this was a case in which this was a blue hemorrhage, and let that physician look at the difference between the image that they're looking at for the patient they're examining and potentially other images that are related in diagnosis to the one that the AI is presenting. So as a whole, this level of explainability is giving that medical professional greater trust in the AI that sits alongside them. And the same concept could be used in really any application, but I like this one as a potential game-changing type application. Yeah, so that was that last piece there. To kind of wrap up the conversation, I did a demo of some of our new kind of perceived technologies in the last part, but here I just want to touch on where we're headed, and really what we're looking for at this point. We want to start a conversation about how AI and machine learning can have a positive impact in the industrial space. So Nick's going to put a poll on the screen here. That's going to kind of just show if you're interested in kind of early access to any of the technologies that I'm kind of going to talk about here. Specifically, we do have a generative kind of AI-based chat assistance for maintaining industrial assets. But when I look at explainable AI in general, I look at it in kind of 5 main pieces. With this technology, we hope to better assist the industrial world in collecting data. We do that already with our GraySense line of products, providing wireless sensors that can capture data from pretty much any industrial asset and bring that to the cloud. But we also can bring in data from a SQL database or a PLC or a SCADA. So that's kind of thing number 1. Thing number 2 is we want to help analyze that data. So again, our focus historically has been on vibration-based problems, detecting issues in either bearings or other kinds of rotating defects that occur in those sorts of assets, and then being able to provide that as an additional level of information to the sensor data that's being gathered. From there, we hope to bring those kind of predictive algorithms I talked about earlier into commercial practice, so you can take that data that you've been gathering and do forecasting for how that particular piece of equipment is going to perform in the future. The 4th bullet point is assisting kind of our customers in maintaining their assets. This is the demo I showed last time, where we can bring conversational AI alongside a maintenance team to give them a better ability to identify defects in their facility and then resolve those defects, and lastly, report on kind of that root cause analysis or remediation actions that were taken to fix that problem. And lastly, this couples with what we just talked about with explainability. We aim to help customers trust their AI, right? So building out tools that are going to help provide clear and concise model explanations for any AI in that facility. So again, this is a long path. This is not a fully articulated solution at this point, but we're looking to start that conversation with folks moving forward. So with that, I'm going to stop talking myself, and we'll see if there's some questions here that folks would like to have answered. So let me pull up the chat bar. Okay. So first question I'm seeing here: do Netflix and other social media have reliable machine learning sites? So I'm assuming that question is whether. Well, I'm going to answer it in twofold. I'm not sure which way this went. So first of all, they have a tremendous amount of data, and access to a tremendous amount of data makes the underlying predictive algorithms better. Now, that said, they also have a rather open-ended problem that they're trying to solve, where they're giving recommendations. So being able to deploy that effectively, I think we're all familiar with the level at which these sorts of content recommenders can do what they do. In terms of data reliability, I can't answer that. I would assume that they are under watch, and all your data is kept as private as possible. But I can't speak for those companies. A question that kind of follow on there was, our inputs, do they have a minimum amount of data necessary for an input? That's a good question. I'm not sure I touched on that, at least in this part 2. The more data we have to build a model, the better. And in a lot of cases, specifically in the predictive maintenance case, we just don't have enough data. We don't have enough failure information to be able to build a really sophisticated model that's able to do a super accurate job of predicting failure. There's a lot of techniques to aid that. We use a physics-inspired approach that brings physics into the equation and lets us run with less data than we might otherwise need. There are data augmentation methods that allow you to take what data you have and build kind of synthetic data that sits on top of that to make better decisions. But in general, the more data you have and the cleaner that data is, the easier it's going to be to build a really effective AI platform. So yeah, this is a good question too. If we have data from a different plant, is it applicable? The answer to that is maybe. So if you have two exact assets, I'll talk about vibrating assets right now. If you got a pump in plant A and a pump in plant B, and they're exactly the same model pump, it is very likely that a model trained in plant A will be able to give you beneficial results in plant B. However, there is almost certainly a difference in the operational environment between those two plants, even if it's almost the same application. And so ideally, we can leverage the difference in environment and be able to kind of fine tune the model that we've got over here to fit in this new environment. But it really, depends on the level of accuracy you're looking for. And I will say, if you're looking for 100% accuracy, you're almost always going to have a problem. So, all right. Okay, can AI recommend a work intervention to equipment in order to extend kind of the prior to failure phase of that equipment? The short answer to that is yes. We don't have a technology that does that specifically, but if you think about an artificially intelligent system that learns in the same way you would maybe learn how to play chess, right? We have an action that we could take to try to prevent or obtain some sort of reward in the future. In this case, we're talking about taking a maintenance action. And if we have sufficient number of maintenance logs to build a machine learning model that can say, all right, this action given this data set leads to an optimal outcome, absolutely. The output of that model could certainly be, you need to take this action and there's this degree of probability that prevents this problem. So that is definitely an application. Again, data availability for building that model is probably the biggest reason why it'd be hard to get there. Yep, there's a mention there about lack of trusted labeled data. So that's anytime you do classification, right? That's what I'm just talking about with this maintenance recommendation system, right? If you don't know the labels on the existing data, so it's just a jumble of data and no human has come in to effectively curate it, it does make it very difficult to build these models as effectively as possible. Right. Am I missing anything there, Nick?
Nope, I think you covered everything.
All right. Okay, well, seeing no more questions, I really very much appreciate everyone joining us on this two-part journey. If you have interest in anything that we've been talking about, please reach out to us. We'd love to interface with you on kind of a deeper level. And again, this is an exciting new field, one that we're excited about, and we'd love to have chats with anybody who thinks they have an application that might work here. Yeah, we'll leave it at that, and we'll get the on-demand videos out in the near future. Very good.